Okay, so the other problem I have here is I have yours, something else there, but that's okay. The other thing I have here is I have we give you a shaft with a pulley on it, a shiv, right? That yeah, a little tickle the ribs, right? So it's
Still keeps going.
yes, I think I did get the point there. So okay. Yeah. Humor's got a bit of an edge. Yes,
No, we're not bitter at all.
Sharp tongue over there, right? So but I think we can handle it. So okay. So now there's some. Let's sort of think. This is kind of an interesting problem, and I give you this one because the other one we didn't have to worry about boundary conditions, and this one we kind of look at and go, well, I got things on the ends that look like bearings. Right? Okay, I got things on the ends that sort of look like bearings. Okay, so we might be able to do something with those. Bearings, for the purposes of most of this distortion analysis, look like simple supports. Okay, it looks like a thing with bearings looks like a simply supported beam, right? Because the bearings will allow a little bit of rotation. Right? They're not going to allow very much, but well, they don't want to resist a moment. If a bearing is resisting a moment, it won't last very long. So we assume that they're going to allow a little bit of that to do that. So, okay, we can sort of, and then I have some points where I get you to ask where the stresses are. So you're actually going to have to calculate the stresses in a shaft. You think you could do that?
Yes.
I think you can. I have faith. You remember those equations. The shear stress is 16T over pi d to the third.
Yes.
Bending moment is 32m over pi d to the third. Remember those. Everybody nod their heads like this and go, you remember those? Okay. Okay. Otherwise, I'm going to go, who was your machine design instructor and how do I fire him? Okay. Or maybe it was the
You open the door.
Or maybe it was the quality of the students. Okay. Do I want to go there? Let's see.
You didn't open the
Do
door.
I
for the
fire
instructor.
myself or do I blame it on the students? I'm going to blame it on the students. I mean, hey, take responsibility. Nah, I'll blame it on the students. Right? Hey, look, students inalienable right to complain about their instructor. Professors inalienable right to ignore them and complain about students. Okay, so we can. It's
The circle of life.
Okay. Okay, so let's. I'm going to go ahead and let's be just sort of barbaric about this. We can sketch this. I'm going to go sketch this. I'll make a shiv here. Right, and let's see. I'll make a shiv, and I'll give it some inch dimensions just because that's kind of the mode I'm in today. Right. I like that one better. Okay, so 120 millimeter is about 6 inches, right? And we'll make it 5 inches just to make life interesting. Okay. Okay, so I got a 5-inch circle. I can get out of the sketch, right? And I can extrude that, right? And let's say, I think I said it was 30 millimeter, and that's about, what, 30 millimeter is about an inch and a quarter. Yeah, so let's do 1.25, just to have something. Okay, so I got a perfectly fine shiv there. I don't mean I could model a pulley on it and all the rest, but since they didn't include any details, why in the devil should I? right? They didn't put any details in it, why should I? So, okay, and now we need a shaft. Yeah, shaft, because we're gonna get shafted here. Yeah, I'm working on it here, I know. Okay, so I'm gonna pick a plane here, right? And then I'm gonna sketch again, right? And I'm going, because I'm hard out, that worked so nicely last time making circles. I'm gonna make another circle here, right? And I'll dimension it up. And let's put a dimension on that. And let's see, it's about 3/4 of an inch, right? 0.75, about 75. Okay, so I got a perfectly fine shaft there, right? I can exit out of the sketch, and I can then go, I'm going to extrude that to, and how far am I going to extrude it? Well, 100 millimeters is like 4 inches, right? So it's, and then I can go the other direction if I want to, and I'll also extrude it 4 inches. And I got a thing with a shaft on it. Aren't we having hard problems to model these days? Let's see, you had to draw not one, but 2 circles. Okay, so
hard.
I am, it's challenging, I realize that. Okay, so now, we've got that. Shoot, that modeling was easy. So you're gonna get done with these all day today, and you won't have to mess with them all over the weekend, right?
That was the best response.
Someone doesn't trust their instructor. Yes. Okay, so we got a new study here, linear elastic. I got some parts here. I'm gonna make it out of steel. So we go here, there's some 1020 steel. That looks like 1020 cold rolled. That's a fine thing to make it out of, though the shiv is probably not made out of 1020 cold rolled steel, but doesn't really matter. Okay, now, so we've got it, it's got some material on it. Now we need to do these darn boundary condition things. Okay, boundary conditions. Guard. So what am I gonna do? Well, I got 2 things that look like bearings. Well, maybe if I fix the ends of it, right? Maybe if I fix the edge of it here over here. So let's go see what I can't do if I fix the geometry, not just geometry, but some advanced fixtures. And we've got on cylindrical faces, let's try to use reference geometry just for giggles. So I'm going to try to fix this guy over here, right? And I'm going to actually show you a little trick that's something they did nice in SolidWorks. If I go for, this is the edge I want to fix, right? In this first one, I'm just going to fix this outer edge. And in this one down here, I get to decide what my reference geometry is, what I want to refer to it as. And if I pick a cylindrical thing, you notice that all of the things I get to fix it to down here, or reference it to, are now all in cylindrical coordinates. Right, so I can stop it from rotating and translating and all those kinds of nice things, right? So this one over here, I just want to stop the axial direction, right? On this end here, all I want to do is I want to stop it from moving in these directions, right? It's allowed to move this way, right? It's allowed to twist. Right? It's not allowed to move in the radial direction. because then it would take off into space somewhere, right? Okay? Does that make some sense? Sort of see why we're doing it here? Okay, that's like a simple support, right? That's the equivalent of this, right? Right? Because all it's doing is supporting it this way, right? And this way, actually, because it's the radial, right here all the way around. It's not supporting it from going in and out this way. That would be the axial direction. It's also not preventing it from twisting, which I certainly don't want it to do because I'm gonna have to put a torque on this end. Right? Okay? So that's not a bad one. Let's just try this. And then let's go over to the other end. Okay, I'm happy with that, so I'll say that one. Go to the other end, and we're gonna have to do this one a little bit differently, because we gotta fix all the degrees of freedom, right? So let's see, we'll do advanced fixtures again. I'm gonna try that edge again, because I had some luck with that. I'm gonna reference it to cylindrical geometry. In this particular case, I'm gonna stop it from, well, I'm gonna have to do kind of like all of them, right? I gotta stop it from going, I gotta make my bearing support. That's the radial one, right? That's the supporting it. But I also gotta at least pretend to carry the torque. Now, hopefully the torque won't get here, right? Because hopefully the torque will go away, because the torque isn't on this part of the shaft. Right? The torque comes in from the other end and goes out at the sheave. Right? That's the problem statement. That comes in, that comes out the sheave. But they won't balance out exactly. When we sum all the forces, they won't balance out.
So is this the free end or is this the end with the clutch?
This is the free end.
Oh, okay.
Okay. Yeah, this is the free end. Yeah, so we're gonna stop it from rotating as well. Okay. Now I gotta do something to stop it from sliding axially. Okay. So somewhere along the line, right now I have it fixed, so it won't rotate in space, because I just fixed the rotation here, and it can't move radially in space at either end, because I got both of those fixed, but it can still translate axially. So I gotta stop that somehow. Well, shoot, let's try that here and see if we like it. We probably won't, but let's try it here and see if we like it. Sometimes you experiment with these and see what they do. Okay, so we've got boundary conditions on the ends that I'm not quite sure if they represent the bearings, but it's what we have, right? Now we get to put torques on them.
Yes, so the left end, Dr. B, could we just use the fixed geometry option, which by default fixes everything?
Well, hold on. Let's see. Okay, I'll answer that a little later. Okay, let's go see what we do. So anyway, I'm going to put a torque on this other end over here. I got about I got a force on it, so we can put some external loads. I got a force, and I'm probably going to put the force on, let's say, this surface here. And it doesn't want to be normal, right? It wants to, I gotta select a direction. So gotta go pick a direction. I don't have any planes, so let's go pick how about let's pick the front plane, right? Just because it gives me a plane to direction on. And then I'm gonna pick something normal to the plane. How about let's go the other way just for giggles, doesn't really matter, but it sort of looks like our drawing this way. And I gotta put forces on it. See, we've got about 2,400 newtons. So that's 2,400 newtons. Let's say that's like 400 pounds probably. Let's say 500 pounds. Okay. So you guys have the easier thing. So that's the force going that way, right? And then I can put a torque on it here. The same thing, we'll put a torque, right? We'll put a torque on this guy here, that same force over there, right? My reference geometry, I can actually use the same surface for.
How did you get the force to do what it's doing?
You select the direction. You don't want it normal to surface, you want to select the direction. And then you have to go pick a reference for it. So in the one underneath, just pick I picked the front plane. Okay? And so this one I'm gonna do, let's say, 1,000 inch-pounds, that's probably about right. Okay, so I got a torque on here, 1,000 inch-pounds and 500 pounds. And that's certainly the load on it, right? But I don't have the load coming into it now. I don't have the load that's coming in, so I need to put the load that's coming into this. I'm gonna come over here on the end of the shaft. I kinda like to put it on the edge, but if I try to put it on the edge, it's gonna be unhappy with me. Cannot apply to edges, torques to edges or vertices, so I can't apply it to the edge. I'm gonna have to apply it to the end here. And I think that torque's going the opposite direction of the other torque. Right, the other torque looks like it's going around the other way, so we got the torques going the opposite direction, they're the same magnitude. That's pretty good. I gotta have torques that are equal and opposite, right? Because that's where the power comes in here, and it's gonna go out there, and that torque's gotta be equal and opposite. Right. And then I got the side load on the shaft from the belts. Now, probably isn't the best way to do it. In fact, almost certainly isn't the best way to do it, but it gets us a place to get started, right? And we'll see if we like it or not. Okay? Yeah.
It doesn't look like the torque is equal and opposite based on the values that we have. The moment.
Just deep. Is the torque equal and opposite? It has to be, or the speed isn't constant, right? I mean, they have to be, or it's not in equilibrium.
I forget it's statics.
Not allowed to forget statics. Engineers are not allowed to forget statics. Okay, so I'm not sure I like this model, by the way, but let's go take a look at it. And so we can go ahead and mesh this up. Again, I'll run the density down just to see what happens. Right? We got a mesh, not a real good mesh, but we got a mesh. Right? We can run it and see if it likes it. Okay. Okay, well, I got a lot of torque in there, right? So my torque is probably a little bit big. 1,000 inch-pounds on a 3/4 inch shaft is probably a little bit big. We can go look at this, and one of the things I always do before I do anything else is let's look at it and see if we like the results. Do we like the way it looks?
Oh.
Okay.
Say something's fixed that should
Okay.
be fixed.
Yeah. Now this over here is the high torque. So my 1,000 foot-pounds is probably, or 1,000 inch-pounds is more than it should be. So I'll have to make that something more like, I don't know. I got lots in the material though, but we can make it something a little smaller. Make it down to where it's a couple 100 inch-pounds, just because that's, I just guessed the value. But I'm not too concerned about this. This looks like a torque, right? I mean, if it's a torque in here, where the stress in here is primarily a torque, what should we expect? We should expect that it's uniform all the way around the outside, right? Because that's what a torque is, right? So when you twist it, the stress is uniform all the way around the outside, and that's all we're looking at is the outside. I mean, I'm not worried about the distortion down here. That's an artifact of the modeling, okay? But I don't like it at all up here. Right? Because what did it do up there?
Shows almost no stress at all.
Well, it should have up there, I mean, by the time it gets to there, what should the stress at this end up here be?
It's the free end, right? Is that
Mm-hmm.
nothing up there?
Should be zero, right? Because what's the bending moment gonna be by the time you get there? Bending moment's gonna be zero, right? Right? The torque up there, there's no torque. So on the outside surface, it should be pretty darn close to zero. Okay? And it also ought to be partially rotated, right? Because when we push this way, this thing ought to make a bend. Right? And what's it doing? Making a bend and it's snaking back. So what's happening? Well, that darn axial constraint is screwing things up, right? It's not letting it rotate in there, right? Okay, not letting it bend in there. So this darn axial constraint up there is screwing things up. And we can tell that by just looking at it, right? It doesn't look right. It doesn't look like what, and believe yourself when you see it. When you look at it and go, no, I'm not really thinking that's what it should be doing. It probably isn't doing what you should be doing, right? It's doing something wrong. And up here, our constraints are kind of bogus. Now, well, okay. Well, that kind of is no fun, right? Sort of qualifies as no fun. So, how do we get out of that one? And expletive deleted. Okay, well, there's all, we can get kind of interesting games we play here. And one of the interesting games we can play here is like, what we have fundamentally, right, was a shaft here, right, with a load and a torque on it here, right? And then we had some supports over here on the edges, right, that we said were our bearings, right? Right? Well, what are we interested in this part? Are we really interested in what's happening with this shiv? I don't really care what happens with the shiv. I mean, is the shiv accurately modeled? No. Right? I mean, if it was a shiv, it's a pulley, right? It'd have a groove in it, or, some details that was to how it was made. Right now, it's just a block of stuff. Right? So one of the things we can try, right, we might try doing is going, and it's always sort of my favorite technique if I don't know what the devil I'm doing. Oh, by the way, I got a torque over on this end over here, right? Some T that's equal and opposite to that one, is let's swap the loads and the constraints. That is, instead of constraining this guy and putting the loads in the middle, how about we constrain this guy, put the loads on the ends? Right? Because the loads won't stop it from bending and doing weird things, right? And can we do that? Well, yeah, we can go through and make the free body diagram, do the statics, and we can constrain anywhere we want, right? Right? I mean, that's the loads that it's putting on there, right? So I think I had, 500 pounds here? 500 pounds, if I can do that. I don't remember how thick I made that darn thing. Gonna have to go back to my sketch, right, and figure out how thick I made it, 1.25 inches, right? So it's 5/8 offset, right? So let's go back to this over here. So what we have is a thing where I think on mine those were 4 inches long. So this guy here is 4 5/8, and this one over here is going to be 3 3/8. So you can do a little bit of statics, right? You've got what do we have over here? We sum the moments about sum of forces at moments at B is equal to 0. That's going to be equal, and I'll make that B and A, right? So we'll have some RA times 8 inches minus 500 times 3 3/8 inches. It's all got to equal 0. And so RA is equal to 500 pounds times 3 3/8 inch over 8 inches. Hopefully I can do my statics. No one's cursing at me yet? What's that? No one.
Hopefully you can.
Nobody's done it yet. You're gonna make me push it in my calculator. Okay, 500 in a 3.75 times, 3.375 times 8 divide, about 211 pounds. So this is equal to 211 pounds. And we can do the other one. Sum of moments by A is equal to 0. That's going to be equal to RB times 8 inches minus 500 times 4 5/8 inches. And then we're going to get an RB. It's going to be equal to 500 pounds times 4 5/8 inches over 8 inches. And that's going to be okay, 500, 4.625, 8 divide times 289 pounds, which now do we believe my statics?
Are you a computer?
I was using one. I mean,
Trust them at some point.
well, how would we check?
Yep.
Did they sum to 500? Yeah, looks like they sum to 500 to me. Okay. I don't even do the formal add, right? I just look at them and go, did they sum to 500? At least with these, I can do that in my head. Okay, so we can go back and do that. We've got forces now. So let's go back. Here we go. Oh, I don't like these guys. I don't like these reference geometries. I'm going to delete them. Yeah, I'm going to delete them because I don't like them. Right? I could suppress them if I wanted to, but I'm going to just get ruthless and throw them away. Right? I'm not going to need that force anymore, that 500 pounds. I'm going to delete that one. And I'm going to need the torque on the end, but I'm not going to need the torque here on that guy. Right? I'm not going to need you, come on. Because I'm just going to need the one on the end here, right? And so what we're going to do is we'll get our fixture, do our advanced fixture. I'm going to fix this outer ring here. I could fix probably anything. It doesn't really matter. This thing's such a big chunk of metal. Anywhere I fix it, it's going to do this thing. I'm going to use as a reference geometry my same face, and I'm just going to lock it all up. Right. I'm going to lock up the translation. I'm going to lock up the rotation, and I'm going to lock up the axial translation as well. So it's just going to sit there. Right? Yep, that's all three of them. Lock them all up. I got 3 arrows here on the top, right? We'll lock them all up, and it actually doesn't really matter whether I do it in polar coordinates or I do it in normal coordinates. When you're fixing all three translations, it's not moving anywhere, right? It's not going anywhere. That thing is going to stay there. So now we need some forces. So we get some forces, and I got one on, let's say, this end over here, right? And I'm going to, and this one is gonna be my, this is the long one over there. So it's the force at A, which is the 211, 211, right? And I'm going to actually want it to be a selected direction here. And I want it to go, I need a reference plane, so I'm gonna pick that front plane. I'll do the top. Yeah, it doesn't really matter. I've got myself all twisted around. Top plane, that's okay. And I'm gonna go the out of plane one. Yeah, I'll reverse the direction. I'll do it as long as they both go the same way. Okay, so I've got that force going one way. We'll do the same to the other end. Another force on that end surface. I want to select a direction. Again, I'm going to select the top plane. Better select the top plane, right? You don't have to, but it's easier to get the out of plane one, right? We'll get the out of plane direction. And I want that one's going that way and that one's going the other way, so I better reverse the direction on this one. That goes the other way, and this wants to be my 289. Okay. Okay. So, what do I have? I've got the torque and the force on here. I'm gonna take that torque down to where it's not so big, because I don't like that number. Make it about 200. Inch-pounds, that'll be a little better. It got so out of control that it dominated the bending stress. So, okay. So we have a torque and a load on this end, and we have a force on the other end. Let's go ahead and mesh this guy up. Got a perfectly fine mesh there, and let's run it and take a look at it. And now I get the top here. Did I get my forces wrong?
You have 1 pound force on.
Oh yeah, -1, that's not a good thing. So yes, that, for whatever reason, that didn't get right, so. So that one needs to be, yeah, that one needs to be, the 211, right? Okay, and is it going the right direction? It's going the right direction, yeah, okay. That'll probably help, right?